Good morning and welcome back to Scientific Visualization, more specifically to filtering and mapping. And then once we finish where we stopped last time, the marching cubes approach, or marching squares to be precise, the marching squares approach, once we finish that, we'll start with a new topic, volumes, scalar volumes. But first things first, marching squares. I went back a few slides, so I want to repeat a couple of things from last week's stream about, well, what is this marching squares thing all about? Well, it's about creating lines, creating isolines such as you see them behind me. So here you see a height field, which is, if you think about it, nothing but a two-dimensional domain where for each point you have a scalar value as a piece of information. When you just think about the height, right? So in the image behind me, you see a couple of other layers, whether it's water or land or some landmarks, other piece of information on top of the height field. But the thing that I care about here is really just the topographical map as a height distribution. So if you think about that, it's just a scalar field. So for every point in space, we are given one piece of information, and that is the height. Okay. So, and here you see other examples of these scalar fields. That's a three-dimensional scalar field here. But what I'm interested in so far is just a two-dimensional cross-section through that three-dimensional field. And then again, we have the situation that it's a two-dimensional plane in that case again. And anywhere on that plane, we're given a particular value. In this case, it's pressure. Okay, here's another one of those examples where we have a three-dimensional field. I think it's a temperature field. Again, it's just a scalar value. It's just one number. And we're looking at cross-sections. These aren't planar cross-section, but the basic idea remains the same. We can map that to two-dimensional manifold. So if we have the situation that the data is given on a two-dimensional regular rectangular grid, we can apply an approach that's called marching squares. Okay, it could also be called marching rectangle, right? I mean, it doesn't matter if the grid spacing is the same, but it's called marching squares. So you can use that approach whenever you have these rectangular grids, or we call them simply Cartesian grids. For other grid types, we have similar approaches, but the basic idea needs to be adjusted slightly, but the overall concept remains the same. Okay, so let's again review what I said the last time. How does this thing work? It's a divide and conquer approach, so it basically processes not the entire grid, but the grid cell by cell. So what is a cell again? A cell is the space in between the known points. Okay, so this here, for instance, is a cell. It's a cell between, in that case, 4 known data values. Okay, so we process the data not value by value, but cell by cell. And that, by the way, means that we will have to reuse values a couple of times, which is true. So the first thing we need to do is we need to choose an ISO value. Okay, so that's obvious, but it's still often forgotten, is that when I want to compute a line that follows a certain height or temperature or pressure distribution, I need to choose that value for the line first. Otherwise, I can't compute the line, right? Which should be obvious, but nonetheless, it's often overlooked when these things are implemented or when I ask about them. Okay, so we first choose, say, a temperature of 20 degrees. Say that's a temperature field. Okay, and it's maybe pretty hot here, at like 100 degrees, and it's very cold here. I don't know, minus 10 degrees Celsius. And here in between, there's supposedly the 20-degree temperature line, and we want to know where exactly is the separation between anything that's above 20 degree and anything that's below 20 degree. Okay, well, in between there's this line of 20 degrees. Okay, so the first thing we do is we process this field, as I said, cell by cell, and each of the points, each of the data points that form such a cell are characterized, whether they are above equal or below the given ISO value. Okay, whether they're, in our case, above equal 20 or below 20 degrees Celsius. Okay? And then what we get is a binary classification. And we can call this plus or minus or 0 or 1 or true or false or above or below. I mean, it doesn't matter. It's just a binary piece of information. And I've written that here as plus and minuses. And then we just look at one of those cells and we throw them into basically 4 different classes. So what can happen? Well, the first thing that can happen is we classified all of the points as pluses or as minuses. So whenever you see one of these classes here, you can always invert the values. That doesn't make any difference. Or you could rotate, for instance, the values. Okay, so if they're all plus, well, obviously they're rotation invariant, but for instance, in that case here, you can rotate it, but it's still in the same class. So nonetheless, let's look at this one here first. Okay, so if all values are above, say, 20 degrees, will the ISO line pass through that cell? And the answer is no. Well, at that point you might ask, well, couldn't it be that there's like 40 degrees here, 40, 40, 40, but it kind of goes, decreases here, and then it increases again. So isn't there any chance that there is is there a 20 degrees region inside the cell? And the answer is no. So why could that be no? I mean, the grid might be too coarse, right? So there might be temperature fluctuation inside. And the answer is no, because we assume, and that's an assumption that this approach needs, we assume that the data can be interpolated linearly or bilinearly in case of a 2-dimensional grid. Okay, so our basic assumption is that the data is supposed to be bilinearly interpolated inside each cell. Okay, so that's something that we get from whoever measured or simulated the data. So if they tell us, okay, you're allowed to use bilinear interpolation inside that cell, then this cannot happen. It's impossible that there's a value above or below, depending on what we're looking for. Okay, so that's our first assumption. Otherwise, we wouldn't even use that approach. So from that bilinear interpolation assumption, we can derive that on a line, we have a linear interpolation situation, because if we bilinear interpolate inside a patch, then this means we interpolate linearly on the sides, which will be important in a second. Okay, so the first thing is everything above, everything below, due to our interpolation constraint, nothing can happen inside. So we'll just reject these cells. Okay, let's look at the next class here. So what happens if one is below or just one is above? Okay, and I don't really care what corner, right? You can just rotate the thing and you get the same argument. Or if that one is above and the others are below, meaning they're flagged as minuses, again, you'll have the exact same procedure. So what happens is, if we have one value that is different from the other 3, then we know that there's got to be a change from along that edge and along the bottom edge here. Okay, so there's got to be a change somewhere here. There's got to be a change somewhere here. Why do I know this? Because of the linear interpolation. If I have a value that is, say, 40 here and then 10 here, if I draw a line, linear interpolation means just along a straight line, then there's got to be the 20 in between. No way that's not going to happen. Okay, so we have to have a change somewhere here, or we have to have our ISO value somewhere here and here. And I can simply connect these 2 points by a line. Okay, so second case, one value different gives us, okay, there's got to be a line here somewhere along those edges. I don't know yet where along those edges, but I know that it's got to be on that edge and it's got to be on that edge. Okay, so now third situation is we got 2 different. Okay, so obviously we can have all the same, 1 different, 2 different, and that's it. There's no 3 different, because that's, again, 1 different. Okay, so good. So we can have 2 different values, and there's now 2 cases what can happen. One is these 2 values are adjacent, so they're either here and here, here and here, here and here, and here and here. Okay, so that's situation 1. And the second one is they can be at opposite corners. So let's look at this one here first. If this is the case, again, we know that there's got to be the ISO value here and at the bottom, so I can simply connect the 2. It's sort of similar to this version here, except that, well, the line goes straight down or horizontal if this would be rotated by 90 degrees. Okay, so now let's look at the last situation here. So if I have this situation here again, I can easily figure out that there's got to be an ISO value on that edge, on that, and that, pretty much on all of the edges. So the thing that I can infer from that is, how should I connect those? Okay, so there's two situations that can happen. So I'm supposed to connect them this way or that way. If you think about the values as height values, okay, let's just deviate from our temperature situation here and assume this is height. Okay, let's say I'm interested in the 500 meter ISO line. Okay, and this here is 1 kilometer, this is 1 kilometer, and those are 0 and 0. Then two things can happen. So either I can have a mountain ridge that crosses here. So that basically means that I have a valley here and a valley here that is separated by a mountain ridge. Or I can have a pass-through 2 mountains. Okay. In both cases, it would look the same. Okay, so it would look the same at those corner points. Okay, so 2 mountains, 2 valleys, but whether they're connected or not, I can't tell directly from those values. Okay, so I need to do something on top of that. Before I get to the on top of that, let's first try to figure out how do we find the exact point location. Right? In all of those cases here, okay, in all those cases, all that I've said so far is that the point's got to sit somewhere on the edges, but not where exactly. Well, since I mentioned we have a linear interpolation constraint along the lines, which derives from the fact that we want to bilinearly interpolate inside our cell, then when we know it's got to be a straight line, we can find that point basically. Okay, so how do we linearly interpolate? We've done this a couple of times now, so I'm not going to repeat the function, at least not on the slide, but it's basically just the starting value times some weighting parameters plus the end value times another weighting parameter, and those two weighting parameters, they sum up to 1. Okay, and they linearly vary. So in general, we say something like 1 minus alpha times A plus alpha times B, whereas A and B are the two endpoints. Okay, so that gives us a line in between the 2 points. So, however, one thing that's also often overlooked here at that point is, in particular when I do exams, is like, oh, you have students tell me, okay, well, you do linear interpolation. So, cool, that's correct. Now, can you write this down? And then some students actually write this down and say like 1 minus alpha times A plus alpha times B. And I say, cool, but that's the wrong formula, right? Because it's the wrong way. This formula that we always employ, the simple linear interpolation, is sort of the other way around. It takes as input alpha, 1 minus alpha times something, plus alpha times the other, right? So alpha is obviously the input, since the 2 points are known. We take as input the position, and we get the value out. But what we now know is the value, and we want to know the position. Of course, this is not impossible to figure out. All you have to do is invert that simple equation or solve it for alpha. But that's a thing you got to do, okay? So basically what we do is we input the value, we input the known, in our case ISO value, and we're interested in alpha. I mean, it's no big deal, right? I mean, you divide by one of the 2 parameters, and then you simply multiply this out. So no big deal. But that's the thing you got to do. And then you know alpha, and you know your position. Alpha is between 0 and 1, and you know your position along that line. Okay, so that's it. Everything's done except for the decision which of these 2 cases to take. Okay, even in that case, we can obviously pinpoint the exact location by that interpolation idea that I just mentioned. So the position of those points is clear, right? It's not clear how they're supposed to be connected. Okay, so let's look at that, what's called an ambiguous case, in a little bit more detail, like literally larger in more detail. So let's say that's our situation here. Okay, so we got pluses on the top left and bottom right, and we got this minus classification top right, bottom left. And I've already figured out where the exact point locations are. Okay, and now, as I said, this is a valid situation, right? But that is just as valid. Okay, so what doesn't make any sense is to have a cross situation. Okay, so you might think, okay, can't I just connect them horizontally and vertically? No, that's not possible. Why? It's again not possible due to the linear interpolation constraint. And if you think about for a second what that would mean for values, how they should behave, it's pretty clear that that is not possible. Okay, so the question is just, is it from that setup, this configuration, or this configuration? Now, how can we figure that out? How can we figure out which of the 2 it is? If that would be our mountain configuration, right? Again, if that would be height values, okay, this would mean, like this situation would mean, I could look straight from one value to the other, whereas this configuration would mean if I would kind of look this way, I would kind of look straight onto a mountain. Okay, so that's what this would mean in reality, right? So can I make use of this analogy? Yes, I can. Because what I could do is, for instance, I could look at the value at the center, right? I could interpolate the value at the center. I take the 4 corner points, interpolate the value at the center using, for instance, bilinear interpolation, which is what I'm supposed to use. Why do I say, for instance, I'm supposed to use bilinear interpolation? Well, because I could run this through our bilinear interpolation procedure, but I can make it a lot simpler by simply taking the average of the 4 points, okay? Because that is the same, right? If you go through the bilinear interpolation function, you would see that what does it mean in the center? Well, I take 1/2, 50, 0.5 this point times 0.5 the top point, I do the same on the other side, and then I combine them by 0.5 times 0.5, but at the bottom line means take the average of the 4 points, which I guess makes a lot of sense, right? So what's the center value? Well, it should be the average of the 4 points, which is add them up, divide the result by 4. So I compute the center value by linear interpolation, and then 2 things can happen. If I take that value, I can also classify it, and it could be above or below the given ISO value. So if it's above, that would mean I just looked at the center and I realized, okay, there's a mountain in my way. And that means, well, I must have pluses all the way here, and that in turn means, well, I should draw it this way. Whereas if I would have classified the center value and it would have been a minus value, meaning it's a valley, then there should have been a valley the other way. Okay, so that's one way how to decide which of the 2 cases to choose. And here is the formula, which is really just average over the 4 values. So that seems like a perfectly reasonable idea. However, it's inaccurate. Why is it inaccurate? It's not completely nonsense. And as a matter of fact, it's been used for quite a while, but it's not correct. Not 100% correct, so to say. Okay, so what's the problem here? If it's not correct, then something in my reasoning that I presented in the last 3 to 4 minutes must be flawed. So what is flawed exactly? I mean, the basic idea is okay. So if there's a valley between the 2, obviously there's a valley between the 2. So that's clear. So what is wrong about my reasoning? And the thing that is wrong is the place that I've chosen. Okay, so I mean, I've chosen the center point pretty much arbitrarily, right? I mean, it kind of makes sense to choose the center, I guess, because if I would have say, let's stick with this situation for a second. Let's say we have 2 connected valleys this way. Then if I would have chosen my point to classify here, the result would be pretty much worthless, right? Here I would have gotten a plus, and that wouldn't have told me whether there's a valley this way or that way, right? I mean, so I guess center makes a lot of sense. It makes a lot of sense, but it's not 100% accurate. And the reason for that is a sort of mistake or an approximation, to be more precisely, that we do somewhere else. So basically, the whole method of connecting these points with lines, that is an approximation. And that leads us to the false assumption that the center point is a good choice to make this decision which way to connect the points. Okay, so it all boils down to what is the shape? What is the actual shape of a line inside a bilinear patch that has a constant value? Okay, so what is the shape of an iso line? And from argumentation, you can probably gather by now that it's not a straight line. It's not a straight line. So what is it then? So what's the shape of an iso line? So that's the basic question. Of course, inside a bilinear patch, right? I mean, it's obviously different from patch type to patch type. We know that it's a line inside a triangle, by the way. But you can derive that idea yourself from previous results that I gave you. But nonetheless, let's look at the shape of isolines inside a bilinearly interpolated patch. So what do we need to do for that? Well, first of all, we need to look at the bilinear interpolation function again. So that's the first line. So this is literally the function that I copied verbatim from a slide presented in the last stream. So this basically just tells us, given the position x and y, what is, and I assume for simplicity's sake here that x and y are between 0 and 1, what is the value at that point? Okay, so if I've given corner values for Fij's, what is the value, what is the height, what is the temperature at a specific point xy? Okay, so that's the first equation here. So what's the second equation? Well, the second equation is simply saying I'm looking for an isoline. Okay, so I'm looking for a line or a function depending on x and y, so that's somewhere in between my object here, that has a constant height, a constant temperature, a constant whatever. Okay, so that's basically what I'm looking for. So now let's combine these two. Conveniently, both left sides are the same, right? It's always f of xy. So I could simply set the two equal. Okay, so I now want to know, given iso value c, that's something that I know, right? I want to know what's the temperature line for 20 degrees, what's the height line for 500 meters. Okay, so that's the thing I know. And then on the left, I still have the same function as before. And let's again look at the values here. What are knowns and unknowns? Okay, so all the f's are known. Okay, those are the values at the 4 corner points. What is x and y? Well, those are the coordinates. Okay, now all I have to do is solve that for y. Okay, so then I would get a function f of x that tells me for that tells me what is the y for a given c. Okay, so now I can do this for you. So here's the result. And this happens if I solve this here for y. So this gives me the y coordinate or any x coordinate of an isoline. Okay, so as you can see, it's a somewhat lengthy function, but it's no big deal. It's just a fraction. Okay, and I can simplify this further because, as you can see, x appears at the top and at the bottom. Okay, there's an x here, there's an x here. There's no way I could simplify this. I mean, I can express it differently and factor the x out in the constant, but nonetheless, it'll stay a fraction. So how do we call fractional function like 1 over x? We call them hyperbolic function. Okay, 1 over x is the standard hyperbola, and then other hyperbolic functions will have a similar shape. So bottom line is, this is not a straight line. Okay, this is a function that kind of looks like this, right? Think about an 1 over x function, right? This is a function that looks like this, and on the other side it looks like that. Okay, so it converges to asymptote, but it's certainly not a straight line. I mean, that's kind of the take-home message here. It's not a straight line. So connecting the corner points via lines is an approximation. We should connect them, if we want to get it correctly done, we should connect them as hyperbolic arches. And that's coming back to our question, why do we even care about the shape of the function? Well, we cared about this because the question was, is the center point a good point to make a decision? Now, if I take those 4 points here and connect them with hyperbolic arches this way, what you can see is that the center point, even though in that particular situation, this should be a connected mountain ridge, you see that the center point is still classified as minus because it just happens to sit at a somewhat unfortunate position. Okay, so it's still connected this way, but I just classified the wrong position. If I would have taken that point and shifted it to here and made a classification, I would have gotten the right value. The question is, how do I figure out that position in between the hyperbolic arches? Okay, well, nothing easier than that. I just need to look at the asymptotes. So a hyperbolic function, hyperbola, always converges towards a simpler function, a straight line to be precise. And this straight line is called an asymptote. By the way, that's the definition of an asymptote. It's a line function to which, or it's a function to which another function converges to. So in these asymptotes, if I compute them, the one for x and the second one, the y asymptote, then at the point where these two asymptotes intersect, I'm safe to do my classification. So all I have to do is compute these two asymptotes, compute their intersection, compute the value at the intersection point, classify that, whether it's above or below, and then I got my decision which way to connect these points. Okay. So any questions about that basic idea? In particular about this whole train of thought. You see, there's a couple of things that I stick on top of each other. And I know, again, from past experience that students tend to kind of lose kind of the idea of what I'm talking about, like, because I'm stacking things on top of each other. I really would only want to know how to connect these red points. For that purpose, I need to figure out what's the shape. For that purpose, I need to figure out what's the asymptote. I need to figure out the intersection. And I need to figure out what's the value there. And I need to make a classification. All I get is a yes or no, like this way or that way. Okay, but nonetheless, needs to be done somehow. So it doesn't look like we have a question. So cool, let's continue. Good. So now that we know that it's an asymptote, we should compute them, and we get the correct decider. So how do we get that point here? How do we get this? Or how do we more precisely get the value at that point? We don't really care about that point specifically, but we care about whether the value at that point is above or below. Okay, so let's call the value beta here. Okay, so just call that value beta, and that's what I'm interested in. I want to know is beta above or below my ISO value to make the decision how to draw, which direction to draw the lines. Okay, so again, let's return to the bilinear turbulent. Okay, so again, at the top, same function as before, so same thing as before, that's a bilinear turbulent, and I've written this here in two ways, just so that you see that it's kind of this is the same as the one on top. So the one on top is the 1 minus alpha times alpha formulation that we sometimes use, and the one at the bottom is the one that I've used before. So what I'm interested in is really just the value of that function that I call beta at the asymptote intersection. Okay, so let's write these two functions down. We have the bilinear turbulent, and we have this function here with beta. So this is actually exactly the same as before, except that I now say beta instead of c. Okay, previously I was interested in what's the shape of an isoline, so I just set this to a constant here, and now I say what's the value, which is kind of the same, but beta is the unknown now. And of course, I'm not interested in all x and y's. I'm just interested in the x, which I call x alpha, and the y alpha, which is just this one x and this one y at the asymptote intersection point. But of course, the function is the same, right? It's still a bilinearly interpolated pitch. The thing that changes is what is known here. Previously, I knew the value of the ISO line. Now I want to know the position of the asymptote intersection, or more precisely, I want to know the value at that position. Okay, so now x alpha, y alpha, and beta are unknowns. Okay? Previously, they were all knowns, right? X, y, or x, y were the parameters of our function, and c was the unknown. Okay, so what I now do is I take these two functions here, these two lines here, and I just say, okay, well then, let's just input x alpha and y alpha into the function at the top and set it to beta. Okay, so this is basically the result what I get if I then take this function and solve it for x alpha. Okay, now I have a little bit of a problem here. Okay, so I have a bunch of unknowns in there. Like I have x alpha, which is an unknown, y alpha, which is an unknown, and I have beta as an unknown. So I can't just say, okay, cool, I'm done. Okay, so how do we deal with that situation? That we have one function and three unknowns. That's a little bit of an issue. And it's no surprise that we have three unknowns, right? We want to know the x, the y value of that intersection point, and we want to know the value that we get at the intersection point. Admittedly, if we know two of those unknowns, we can compute the third, right? If we know x alpha and y alpha, we can compute beta. Right? I mean, we just plug two in and we get the third out. Okay, so effectively we have two unknowns here that we need to somehow figure out. Okay, let's try to get rid of the first of the two unknowns, because This here just tells me for any point, but I'm not interested in any point. I'm interested in the asymptote point. Now, there's the one thing that is very curious about the asymptote that we know is that when we say, what does this function tell us here? It gives us the x value of a, excuse me, it gives us the x value of this hyperbolic function. Now, what happens with the x value, for instance, or what happens to the y value, let's put it like this. What happens to the y value if we take x and turn it into infinity? So I basically look at this function at infinite distance. It's a hyperbolic function, so it converges, we know, it converges towards a certain asymptotic function, okay? So if we let this x approach or this y approach, I mean, it doesn't matter, we will actually end up doing both. So, okay, in this case, let's y approach infinity. So in this case, we look up and down infinitely, but if you rotate it by 90 degrees, you can do the same with x. Okay, so if we let y go to infinity, we know that this function converges to an x value. If we let x go to infinity, we know that the function converges to a certain y. So let's look at what happens if I let, in this case, y approach infinity. So for this, we need calculus. And what does calculus tell us? Well, if y approaches infinity, it shows up 2 times here, right? So it's bigger. So here's a y, right? And we also got a y, well, here. Okay, then if that approaches infinity, all that matters is the factor in front. So all we get is this here divided by that here. So any constants go away. So that's basically it. It's a pretty simple, it's a pretty simple limit that we need to compute here. So what this tells us, the x value, if y approaches infinity, is whatever this here. And that thing, curiously, doesn't contain any unknowns. Beta is also gone conveniently. Okay, so all we have is something that depends on a bunch of f's, and that we can compute. All the f's are known. We repeat the same process, as I said. Instead of looking up and down, we can look left and right. It's the very same thing, and you can see that here. So that's the second function. So this gives us a y value, y alpha. Now we know x alpha, and we know y alpha, and we can take these two values and plug them back into our initial function here, which will give us a gigantic function, right? If I take these two fractions and like throw them in here a couple of times, so here once as a product, right? And they'll appear here, and that's it. Okay, so there's basically these 3 places, product here, once here, once here. If I put this in, I get this thing here. So that's one function. It just happens to be so long that I have a hard time writing this. But you can still see them, right? So there's a product of the 2 versions here, there's one here, and then there's the other one here. And then in the front, there's the tiny constant like Fij that remains. So conveniently, that long thing, if you just start to simplify this, multiply it out, a ton of things cancel out, and all that's left is this short function here. Okay, so that's pretty much all that's left of this function, and that is f of x alpha y alpha. Okay, why is that? Well, because it was it all along, right? It was f of x y here, was f of x y here, so I haven't changed anything. I just plugged in values. Okay. So, what's curious about this function is, what is f x alpha y alpha? We already gave that a different name. What is that? What did I call f of x alpha y alpha? And that's a question. So I'm actually waiting for an answer here. So what do we call that? Just checking if the chat works. Okay, we call it beta. Thanks. Yeah, that's beta. Okay, cool. So we figured that out. That thing we called beta. Why would I care about beta? So let's check a sanity check if someone's still paying attention. So what did I do with that beta? So I'm actually claiming here at that point I'm done. Okay, so I'm actually done. Like next cycle will be next topic. So I'm done here. Why am I done? why do I stop talking about marching squares at that point? Because we interpolate at that point. Well, might be correct. It's kind of hard to tell from the way you phrased this. It was kind of interesting trying to Like you're obviously trying to type this as short as possible. And I need to interpret that short notation. I guess asymptote plus minus is probably probably correct. Okay, so let me just spell this out with a little bit more words. Yeah, so that's the beta is the value at the asymptote intersection point, and that was the thing we wanted to compare to our ISO value, and that's I guess what bike means with plus and minus, right? So we just do a simple comparison, less equal of this value here, the result of that value, to our ISO value, and we know which way to choose. Done. Okay. Okay, so that's it. This gives us the final piece of the puzzle. This tells us how to connect the two pluses or the two minuses. Okay, and we still connect them with lines. So didn't I just say that lines are inaccurate or incorrect? I mean, it depends, I guess, on your philosophical view of the world. And that's true. However, for visualization purposes in general, we would not draw these asymptotes, we would not draw the hyperbolic arches. We can compute them, but what happens is that usually these cells are pretty small, right? Your grid is relatively small, hopefully. So if you would do a pixel by pixel comparison of the final visualization result, you would pretty much get the same whether you draw a line or whether you draw a curve. So it doesn't make a big difference, and usually we don't bother in visualization to actually draw them as curves, but just as lines. Okay, now you might say, wait a second, and that's funny. No student ever said that, but I think a valid injection here would be, wait a second. Like you're literally telling us that those cells are so small that no one cares whether it's a straight line or whether it's a hyperbolic arch. Why do we care then about this situation? If the cells are so small, why do we care whether it's connected this way or that way? If I just claimed it's so small, we can't tell the visual difference anyhow. And that would be a pretty valid remark, and I'm still waiting for a student to kind of raise their hand and ask. Hasn't happened in the last 20 years, so maybe it's going to happen at some point. Okay, but anyways, what's the answer to that theoretical question here? And the answer is actually, yes, it's correct. We'll probably never spot the difference. Side note, there's a ton of implementation that for that reason ignore this asymptotic case. So they just choose, they don't even do the midpoint decider, as the middle point idea is called. It's a midpoint decider, and that's here called an asymptotic decider. A lot of implementations don't even do the midpoint decider. They just pick one of the two versions. Okay, for that very argument. The performance difference isn't gigantic because all we have to do is this little computation here. And then basically do another check on top of that, so you don't really gain much performance. But there's a ton of implementation that still do this correct check, even though you don't see the difference. And here's now finally the answer why. The answer is because sometimes you're interested in computations on top of the visualization. So for instance, you want to know what is the area? What is the area of such a piece that is separated from line to line? Or is there a path from one say mountain to the other? Okay, and for those answers, it matters a lot whether there's a connection or not. Even though you can't see it, you might have additional queries that you want to execute on top of the actual visualization. Okay, so you set a point here and you set a point here and say, oh, like, give me the shortest or the most convenient route. Okay, in that case, it matters a lot whether there's a connection or not, even though you can spot it. And in that case, it doesn't matter whether we connect it with lines or curves. The only thing that matters is that there exists a connection. Okay, so bottom line is, for visualization purposes, if the grid is high resolution enough, it's probably no big deal. For a lot of other computation that are executed, it makes a big difference. Okay, so hence it's worthwhile. In the exercises, and I hope you all attend the exercises, meaning, or you do the homework and you attend the exercise, we'll actually let you do this implementation here. So you'll write a small program on top of the framework that we gave you for the previous exercises, where you're given a scalar field, given a two-dimensional field, and you're supposed to compute ISO lines. And the result will be an interactive application where you can change the ISO value and you see how the lines kind of vary. And you'll also implement the asymptotic decider and the whatever, I don't care decider, basically just connecting them, and then you can flip between the two modes also interactively, and you'll see how there's some cells that will change shape. Even though we use straight lines in that implementation, you still see how you get these changes. Okay, and I highly recommend to do that implementation, to do that exercise, and to do that homework. Okay. Any questions remaining about marching squares? Because, as I said, I'm done with this now. Well, so as for the shorthand remark, well, I mean, the lines are also good at these edge cases, again, because they're so small you can't tell the difference, but I guess I answered that. No. So, do we have any other questions? It doesn't seem to be the case. Then let's continue with 3D. Let's continue with full three-dimensional data sets, scalar data sets. Okay, so what you see behind me is a Mundell bulb. So that's a fractal. It's an extension of the Mandelbrot fractals to 3 dimensions, and that's just an example of a fancy 3-dimensional data set. But of course, there's other data sets around, and we talked about those already. Like, for instance, computed tomography, right? It's a scalar 3-dimensional data set. So for every point in 3D that's inside the range of the scanner, we get a Hounsfield unit, which happens to be a scalar number between -1000 and 1000. Okay, so scalar data sets are all around, and again, visualization pipeline here is a quick remark. So we're at the bottom here now. We're sort of at this mapping and rendering stage still, and as I said, we'll remain in those two. I remain talking about those two parts, about those two parameters of our pipeline for pretty much the rest of this lecture. So what can we do to now display, to render, to visualize a 3-dimensional scalar field? Okay, so as a reminder, 2-dimensional scalar fields, we've got marching squares, which I just talked about, which is probably not the first thing you would come up with, right? So if you're given a 2D scalar field, again, that's a funny thing in an R exam, right? As like, how do you visualize a 2D scalar field? What's the most intuitive way? And I said the most intuitive way for 2D scalar field is just assuming that's a black and white image and just displaying it kind of as it is. Whereas as it is means map the values to grayscale and then display each pixel as a grayscale value. But that's probably the most intuitive way, right? So the second most intuitive way might be, and here it's a might be because I don't know how your intuition works, might be to draw this as a height field. And then maybe the third way would be to draw lines, to draw isolines. And of course, you can combine all of that, right? You can draw the isolines onto a height field and color it according to the height, which is something that we did for the map. Okay, so there's nothing wrong with combining all these three ideas into one common visualization. And that's a common theme here. So I give you a bunch of techniques here, and there will be a lot of techniques to follow throughout the rest of this series here, but there's nothing wrong with combining those ideas. As a matter of fact, most visualization systems do. Okay, so now how do we deal with 3D data? So before I deal with 3D data, I just want to get one thing clear that I've mentioned before, but since, I don't know, just about everyone on this planet seems to have a not wrong conception about pixels or voxels, but a mental idea that is not very practical. Let's put it like this. It's not wrong, but it's just a bad idea. Okay. And this idea is that if I'm given a grid, and let's stay with 2D for a second. I mean, the same problem arises in 3D and it becomes more cumbersome, but let's just do 2D for simplicity's sake for a start. So let's say that's a data field. Okay. Let's just say it's full of colors. Okay. So, or in other words, it's a picture. Okay, so again, let's not make things too complicated. So we would probably call this a picture, a grid of 2D color values. You probably simply call this a picture. And then if I zoom in, it would probably look like this. So, and a lot of folks actually have this idea that I call large or fat pixels. Okay, which means, so you have data values, so you've got blue here, you got brown here, you got yellow here, and then you say, well, okay, that's the yellow pixel, that's the brown pixel, that's the blue pixel, and so on and so forth. And that sort of implies that this is a grid cell full of blue, this is a cell full of brown, this is a cell full of yellow, and you get the idea. And you could do that. I mean, it's not that this is inherently wrong, but it's pretty bad. It implies a couple of things. So the first thing that this implies, this sort of whole idea, is that space is full. I mean, there's no place in between two pixels here, right? Those pixels fill up the screen completely. So there's pretty much nothing I can do with that. I can draw it this way. If I were to draw this as a height field, right, I would get a bunch of bars. Right? Let's say this is a color-coded height. Let's say this is temperature or something. So this would be pretty cool, and then red would be pretty warm. So all I can do is I can draw this as bars. I can draw this as blocky things. Why? Because, well, I can't have a smooth transition because this is full, this is all blue, and this is all brown. So there's no place in between. Okay? So if you have this large pixel kind of idea in your head, which pretty much everyone has, then this implies a lot of, well, unfortunate things. So, while not being completely wrong, you can do it this way, but it's probably not a good idea. So, let's think about data differently, and that is a very important thing. Let's think about the data, and I've already done this with the marching squares, but I'd like to repeat myself here because it's such an important thing. Let's think about data literally as sample points. I mean, because that is what they are, like color or height or temperature or whatever. They're sample points at points. I mean, it's called a sample point for a reason. Right? So our pixel is a infinitesimal small point. It's a known value of a only partially known thing. Let's keep this as general as possible. Okay, so we have a thing which we might call reality, height field, temperature distribution, pressure distribution, I don't know, or simply picture. I mean, the world is continuous except for that quantum thing. But other than that, it's pretty continuous. So if I take a photograph, what I do or what the camera does is it samples the world at certain points. So I get color values here. But of course, in between something happens. Okay, so it makes a lot of sense to say, well, our samples, our pixels, or whatever we want to call them, are points, and in between, there's the great unknown. Okay, so in this great unknown in between, we call this a cell. Okay, so very important thing, because otherwise you'll have a hard time understanding all that's going to follow. You can, and even if you have this understanding, you can still sort of get a visualization of the world that looks like this. There's nothing wrong with it. All you have to do is say, my interpolation function of the great unknown in between is nearest neighbor. So I just choose to interpolate any value in the great unknown as nearest neighbor. So I simply, for this value here, I pick the closest neighbor, which happens to be this one. Or for this point here, I pick the closest neighbor, which happens to be that one. If you do this, if you have that kind of idea in mind, and you apply a nearest neighbor interpolation, you get this here. Well, shifted by half a pixel to be precise. But other than that, you can generate a visualization at that one with this idea. But you can't generate a smooth version with that idea from before. It only works one way. So this here is way more flexible. Okay. And it's say a lot more accurate and to the point. So kind of like quantification of color. Yeah, well, okay, so that's an quantum colors that pop up from point. Yeah, sort of. Yeah, that's kind of the idea. So I said I want to start with 2D but get to 3D. Why did I not go 3D all the way? Because, well, if I do the same thing in 3D, you don't see anything, right? That's like, this is why I do an animation here. Let's do it again, because you can see that's a brick, right? That's a single brick. But as soon as I draw this as 1D, 2D, 3D, all you see is a mess of lines, right? So this is just as a side note. Why do I start with 2D? But the concept is the same. As you cannot see here on purpose, is, again, I think about a grid not as this is one pixel, this is one pixel, but I think about this as 8 values, and the cell is in between. Okay, so important thing, keep that in mind. Good. Now we got that part straight. I don't think there's, well, if you have questions, go ahead. I don't think it's a big thing to understand. It's just a big thing to kind of point your mind to, okay? So it's not complicated, but it's something that you should keep in mind. So now again, two pieces of vocabulary, shape and appearance. What are these two things? So if we have a data set, it has basically two properties. So one is the shape, and the other one's the appearance. What's the difference? Well, shape is pretty much the domain. Like for instance, this here is, if I recall correctly, that is an exhaust outlet out of an engine. And you see there's probably 4 cylinders here, and you get the flow of the exhaust. I think that's what it is. It doesn't really matter much, but the thing is, what we're interested in is the distribution inside those pipes. So the shape in this case is not a cube. It might be something else. It might be some more complicated thing. And then the appearance is what we're really interested in is, like, for instance, what is the distribution of temperatures or gases or pressure or whatever inside that pipe. Okay, so just so that you know, whenever I talk about shape, it's about the outer limits of our domain, and appearance is what's going on. Okay, so and most often in our case, the shape is actually a square or a cube, okay, or a brick rectangle, if it's not the same in all directions. But nonetheless, it happens from time to time, in particular when I start to talk about tetrahedra. Good. So volumes. I said we want to move to volumes. We want to move to 3-dimensional data sets. I already shown you this Mandelbrot thing. So here's a couple of other examples. So there's a cloud, obviously, on the left, and there's a fire as a fire simulation. It's a flame simulation, a combustion simulation to be precise. And what's important about these two data sets, that's why I picked them, is if I were to try to convert them into a geometric object, okay, so I want to know the surface of the cloud, or give me the surface of the fire, you would probably run into an issue, and that's, what is the surface of a fire? Or what is the surface of a cloud? I mean, it's pretty clear to say that's the surface of a table or the surface of a car. Okay, that's fine. But what's the surface of a cloud or a fire? Okay, so bottom line is, I mean, you can define these things. As a matter of fact, we will later on. But it'll take a lot of kind of going through hoops to make such a definition. There's no, like, obvious definition of the surface of a fire or a cloud. So there are things, there are phenomena, simulations, measurements, whatever you want to call them, but there are things that per se do not have a surface, okay, that are just cloudy in nature, like literally a cloud is cloudy in nature, right? So that are volumetric in nature. There's other examples here which are probably not that obvious that they don't have a surface. Okay, so what we've got here are humans. That's a human, that's a human. Let's make it bigger. Human, okay. That's an opossum baby, life form. And that is a mixture simulation of two fluids. Okay, so for some of these data sets, you can probably come up with surface. As a matter of fact, I computed the surface here of this opossum baby. So that is a surface. It's sort of it's kind of natural to say, well, okay, that's a living life form. It does have a surface. Cool, works. We could do the same for humans, right? I can obviously compute the surface of a human being. For this mixture type of thing, it might be more tricky, okay? So at some point, so if this is, say, oil and water, and you can think about the simulation as simply being two fluids, oil and water, and then I remove the interface between the two, and one rushes into the other. So for instance, oil rises, and then it creates these plumes, and that's what you see here. So for oil and water, I can probably also have an interface, okay, because the two liquids form a clearly defined interface. But there's an interior as well, okay? So for humans, we do have an interior, right? So while there is this notion of a surface, there's still interior stuff like organs, bones, fat, whatever, right? This whole interior mess inside a human. And the same is true for this opossum here. It also does have an interior. So while sometimes we can define a surface, and there's an intuitive way to define the surface, it's still not necessarily all we're interested in. Okay, if I'm interested in the surface of a human, I don't have to go through the trouble of X-raying them or CT scanning them. right? I can just take a photograph, or if I'm interested in three-dimensional geometry, I do a scan. I do, for instance, a laser scan, which is something that is done also in the clinical practice, right? Sometimes humans are just being laser scanned. So for instance, if you have backache or something, right? Then depending on the level of sophistication of the doctor, they might perform a 3D scan and try to analyze your posture with software and algorithms. Okay, so sometimes we actually do a CT, we do surface scans also of humans for clinical purposes. Okay, so nonetheless, we're sometimes interested in the interior, so we're dealing with the volumes. So in here, I kind of briefly try to give you an overview what we can do with the volume. So when I have volume and I want to display it, we call this concept volume rendering. Okay, so you want to render volumes. And there's basically 3 ways, or there's kind of 2.5 ways to render volumes. The half I painted that in gray. So there's direct and indirect volume rendering. And then there's slicing, which is kind of cheating. Okay, so instead of rendering the volume, I can say I just slice this. I cut this into like literally slices, just like a sausage. And then voila, my volume is just 2D and I can just employ 2D techniques to it. Okay, so I would say that's cheating. No, it's not. So sometimes it's actually an interesting thing to just look at specific slices to get a better insight. But it's cheating from a point of view that we know how to deal with 2-dimensional scalar data sets, right? Pictures, height fields, isolines, or some of those combined. So that's why I put this in gray, and I'm not going to talk about this any further because I already explained how to deal with that. So what's left are these 2 things: direct volume rendering and indirect volume rendering. And the 2 can be done, again, by multiple approaches, okay? Curiously, there's a method called slicing for direct volume rendering, and those 2 are not the same, okay? So they're just, unfortunately, both called slicing. But nonetheless, I mean, they're related, but they're not the same. So for direct volume rendering, we basically have raycasting and slicing, and for indirect volume rendering, we have marching approaches, as in marching squares. There's also a marching cubes, which I'll talk about later, and we have the approach that's just called other approaches. Okay, so let's look at this direct and indirect volume rendering in a little bit more detail, and let's start with indirect. Okay, so here's a visualization of a C60 molecule full array, or sometimes referred to as buckyball. It's just a big molecule of 60 carbon atoms, and that's the electron distribution here that I visualize. And for that, I can, for instance, compute a surface. Okay, so for this molecule, even though it's not very intuitive, more in how to compute these surfaces later, but I can say, okay, well, give me a surface of those atoms. And there's concepts of surface, there's van der Waals surface, and so on and so forth. I don't want to go into the chemical details, but the thing is, I can compute this kind of surface-like thing, and that's indirect volume rendering. So I take the volume, and somehow, and that somehow can be sometimes a little bit unintuitive, but I somehow turn that into a surface. Okay, so whatever the surface means is very specific to the data. Right? But so for instance, for a CT scan, I can compute the surface that corresponds to the skin, or more precisely, the interface of matter of tissue to air, which is what we generally refer to as skin. Or I could compute from a CT scan the surface of the bones, or more specifically, the interface of bone to other tissue. Okay, but that's indirect volume rendering. Why is it indirect? Because, well, we don't take the volume, we turn the volume into something else, namely a surface, and then we render the surface. So that's why it's called indirect volume rendering. Okay, an example for an approach is marching cubes, and notice the similarity to marching squares. As a matter of fact, marching cubes is exactly the same, just in 3D. Surprisingly, when I'll talk about that in 1 or 2 weeks, 90% of the participants have forgotten marching squares, and it seems like it's completely novel. But nonetheless, it's the same idea in 3D that just makes a few of the computations a little bit more complex, but it's really the same. Okay, so that's indirect volume rendering. As I said, I'll talk about that in a bit. So next thing is direct volume rendering, okay? And in direct volume rendering, we'll render the volumetric thing directly as it is from the volumetric data, okay? So, and that sounds more simple than it really is. If the data that I'm given is, say, I don't know, a fire or a cloud, I could probably do this relatively directly. If my data is, again, this distribution of, or this probability distribution of electrons, like flying around the carbon atom's cores, right? Then direct is kind of a weird thing, because like, what does it mean to look directly at the volume? I mean, that's a probability distribution. Like, what does a probability distribution look like? It doesn't look like anything. I mean, as a matter of fact, at an atomic level, looking doesn't make any sense, okay, because it's way below the wavelength of light, so it doesn't have an appearance, right? So it doesn't interfere with light, so it doesn't have an appearance at all. So the thing is, we have to kind of make a little bit of a mental jump here. Okay, so we have to take the data set, and whether that's a TT scan or an MR scan, a combustion simulation, I don't know, a molecular data set. We first have to make this step to say, okay, well, let's pretend that data set is not an MR data set, but it's I call this here semi-transparent gel. Let's pretend it's some object that is partially translucent, like a gel. And then let's look at the physics of what this gel would look like. And then let's somehow map the Hounsfield units or the probability distribution to properties that this gel would have. And then I can tell you what a gel with those properties would look like. Okay, so big mess, you might say. Well, it turns out it's relatively, usually it works pretty well. But we have to somehow do this mapping from, and that's, as a matter of fact, that's the mapping process that is in my slide at the beginning of every lecture, right? We have to map those quantities, the visualization quantities, to some visual properties, okay? Now, what's a semi-transparent gel? So these are actual photographs of a matter called aerogel. You can find them on the web. I tried to buy a piece of aerogel, but it's actually pretty hard to come by, even though it's nothing super unusual these days. It's used for insulation purposes, but it's actually pretty hard to get, at least in Germany, from online stores. So maybe at some point I'll import some from the US to just show this in reality. But it's a really cool piece of material. It's made of you can make aerogels of multiple materials. It's often made of glass, but it's a material that is almost 100% air. So it's something like 99 point something air. And in between you have some molecular structure left. And the resulting matter is pretty translucent, super lightweight, because it's almost entirely air. You can imagine that it's very lightweight. And it conducts pretty much it doesn't conduct pretty much anything, right? So for instance, heat is transferred just very badly through this material, okay? So then you can do these fancy things. You can, unfortunately, it's very fragile. You can imagine something that is 99% air to be like easily breakable, right? And then that you can see from the top image, right? You probably noticed that there's a lot of, the edges are broken off, right? So if you touch this, it usually falls apart. You got to be very careful with that. But the bottom line is, it's a good insulator, and it's used. I think it originates as usual from some sort of accident, but it's been used in spacecraft. But today it's used in installations for Windows, so it's nothing highly unusual. Okay, it's called aerogel. The reason I talk about this is because this is a pretty cool example of an actual existing thing. So even though they look a little bit like sci-fi, those are photographs. Okay, those are not rendered images. Those are actual photographs of an object that is extremely translucent and that interferes with light. So we can take the physics, we can take the optical properties of that thing and just map our properties of our data set to, for instance, aerogel properties, and then figure out what would aerogel look like, and then render it. Okay, so that's kind of the basic idea. Yeah, in a sense, it is a point cloud, right? It's a grid. It's a grid of whatever you made it of. I think, as I said, glass. I think it's like a very common material, but you can make aerogels of pretty much everything. So, and if you want to look for that, just search aerogel on YouTube or on your favorite platform. You'll find a lot of fancy videos about it. It's a cool thing. So what does that have to do with volume rendering? Again, we want to use that. Why are we interested in this whole process anyhow? Because we're interested in interior structures, right? In inner structures. Okay. And as I said, we can slice things, right? We can simply cut things into slices. I mean, virtually, not physically. That's why it's called computed tomography, because you don't want a tomography performed of your body, right? I mean, if a doctor slices you into pieces and then says, "Oh, I've just figured out how your fraction, how your bone is fractured," it's probably not the best approach. So you want to compute that tomography, not actually perform it. Tomography means cutting into pieces. Okay. So one way to do this is to compute these pieces. That's what we call slicing. Here you see a human leg, and you see what a slice through looks like. So you see basically bones in the center, the white stuff, fat outside, and then muscle, the blood-filled tissue in between. That's one thing. Isosurfacing would be indirect volume rendering, just rendering the surface of, say, the skin or the bones, and I can render both, right? I mean, I can render both, make them transparent, but still I wouldn't see the stuff in between. Okay, so what's probably a better idea, or sometimes a better idea, is to like visualize the whole thing directly. Okay, and what's curious about this, if we do this direct volume rendering, we'll end up with methods that allow us to also recreate these images. So in direct volume rendering, we can also highlight surfaces, we can also do slicing. So it's kind of it allows us to do a superset of those operations. So another two terms that I need to mention before we can get started, that's classification and that's segmentation. So those two things are often mistaken. So I just want to go over them in a little bit more detail. So classification is taking properties of the data, density, temperature, whatever, Hounsfield unit, and mapping them to visual properties. Okay, so that's what I've been talking about all along. There's also segmentation, and that's grouping values into, well, groups, into clusters. Okay, so classification is usually done by the means of a transfer function. That's a function that takes that weird thing, the Hounsfield unit, the temperature, the whatever humidity in the cloud, and maps it to something that a aerogel or similar material would have, and then this would result to a certain visual appearance. Okay, so for a cloud, we could also do this directly, right? We can take the parameters of a cloud and turn it into what would this cloud look like. A cloud actually has an image. A fire also has a visual representation. What's interesting though is that those visual representations might not be the things we're interested in. All right, so also for a combustion, for a fire, maybe we don't want to see this like rendered photorealistic. We want to see more than we could see if we snap a picture. Same for a cloud. So keep that in mind. Even for an object that does have a visual representation, that might not be the desired visual representation for a visualization. So here's an example. That's a tooth data set. Put myself in the center. So this is what I get if I would do one transfer function. This is the tooth inside a CT scanner. And on the right, you see different transfer functions. So in this case, I, for instance, have chosen a transfer function so that all the properties that correspond to air are gone. Remember transfer function? I already had transfer function in a previous slide set when I talked about the filtering process. Okay, so I already had this human body lying on a bench with two different transfer functions. That's the same idea. That is the transfer function. That thing transfers properties from the dataset to visual properties. And those visual properties in this case are simply two things: the transparency, or more precisely the opacity, which is the opposite of transparency, and the color. Okay, and here I made a lot of the stuff that is pretty much air. I made that opaque, and here I made it not opaque or transparent. And then I assigned different opacities and different colors to the interior structure of that tooth. So how does that work? Just in a nutshell, we'll generally use a fourth parameter, and those following a couple of my other streams know that I talk a lot about alpha, about that thing that can be used for opacity. That's why I put this here in parentheses. But here, for simplicity's sake, we'll just say the fourth parameter is opacity. Okay, so we'll have usually four parameters in our transfer function as output. Input is our value, our scalar value, right? Our Hounsfield unit, our temperature, our pressure, our whatever probability of an electron flying there. And the output is a quadruple of red, green, blue, and an opacity value. Okay, So that's usually stored as simply quadrupled, and we just call them RGBA for simplicity's sake. So here's again the image that I've presented before. Right, so that's a participant here in a clinical trial, and she has been scanned, CT scanned. And as you can see, I can take the very same data set. So that's just one CT scan. Oh, let's maybe just keep myself here. That's just one CT scan of a participant. And here I've chosen the transfer function on the left to highlight the interface between a tissue and air. And tissue can be a lot of things. So that's like the body's tissue, but that's also the bench tissue. And there's a pillow here that is also highlighted. And I've actually, if you look at the transfer function closely, so that's the transfer function here. Okay, so the white function here, that is the assignment of the scanned values to opacities. As you can see, I pretty much said, never mind this bump here for a second. I pretty much set everything to 0 to transparent that has a very low value, which is, for instance, air and all that stuff. And then I have this gradual increase towards completely opaque, and this is roughly where the transition from air to skin or air to tissue is, okay, to body tissue. So this is why a body is opaque and everything around is transparent. So now about this little bump here. So I introduced this little bump here just to show you that I can not just highlight one surface. I mean, that's the whole point. We want to visualize the whole thing, or at least parts of the whole thing. So this bump here means that also lower values that have a lower Hounsfield unit than body tissue should also, some of those should also be visible, not the super low values, which are really air, but some of those I want to visualize, but I want them to be relatively transparent. So they should be see-through. And if you look very closely at that image, you can actually see that this highlights the clothes. So you can still see the clothing that this participant was wearing, but it's very transparent, right? And it's white. So the color is yellow. So on top you see the color assignment. The color is yellow for the body, and because it's transparent, it's kind of hard to see here, but that part is white. Okay, so the result is white clothes. So that's kind of the Superman, I don't know, X-ray vision. Like, I mean, it's literally X-ray. So that's kind of Superman's stalker X-ray vision, right? So, but what I can also do is I can take the very same data set. So only one scan needed here. And then what I do is I just shift, left. So I shift everything to the left. The hump at the beginning is where white, yeah, so that's where white is. So this, you can actually tell if you would follow the red, green, and blue curve. You should see that they go up. So the red, green, and blue curve define color, and those kind of go up here. So this is why that part is white. Yeah, so this white is white. So, but more about colors later on. Let's just focus on the transparency for now, or opacity. So what I did here is I shifted everything a little bit to the right, right? I mean, I changed the shapes as well, but you see this kind of bump is a little bit to the right, and also this very steep incline is to the right. So that means that I now focus on more dense materials that have a higher Hounsfield unit. And what do I get as a result? Well, I now get the bones is pretty much opaque, and the skin, or this kind of tissue air transition, like that is now very transparent. And then I also played around with the colors a little bit to make it look creepier. Okay, so but the bottom line is, what I do here is I map things that do not have a visual representation, right? I mean, those are, I mean, it looks like a human, right? It looks like a human female. It looks like the bones of a human female, because it is. But what I show here is I show the density of the material, or the X-ray absorption characteristics, which corresponds to the density. But anyways, let's stick with X-ray for a second, right? I show how do different tissue types absorb X-rays. And I display this as if it would be a thing that we can actually see. Okay, so that we can see. I mean, we can't look inside a human, but we can see the ether. It becomes more apparent when we, for instance, introduce a contrast agent into a patient, right? If you do a scan and you introduce a contrast agent, so you basically inject a liquid that has certain characteristics, for instance, absorbing X-rays pretty well, like, I don't know, gold, for example, has this property. So you inject gold into the human body, it flows around, and then you can suddenly see vessels. Okay, so this, what you see here, looks like a human, and it is a human, but it's not what you would see. Like, this is literally what Superman would see if he or she would have, Superman, Superwoman, I suppose, would have an X-ray vision. Okay, so it's something that corresponds closely to our actual perception of a human surface, but it's not. Okay, important distinction between the two. So, one final sort of thing about the transfer function, and that is, now I said we don't want to have this fat pixels, we want to have those small values so that we can interpolate in between. Now if I apply this transfer function, I have two, I can choose between two ways how to do the interpolation, and both are valid, so there's no right and wrong here. What I can do is I can first apply the transfer function to my original sample points. So instead of dealing with Hounsfield units, I can just apply the transfer function and then interpolate color opacity quadruples. Or I could first interpolate the values and then apply the transfer function. Okay, so as I said, there's no right or wrong. It's just two things that we can do. We call them pre-shading or post-shading. Again, shading has nothing to do with shadow. Shading means filling things out. So we either do the application of the function before the shading or post after the shading. Okay, so those are two different. So here's the visualization of the same data sets using pre-shading and post-shading. And if you look closely, you'll see a difference between the two. Okay, so again, there's no right or wrong. So there's situations where post-shading makes more sense. And there's situations where pre-shading makes more sense. To give you an example, for instance, if my data set is a classification, it's a segmentation result, and I'll, in a minute, talk about segmentation, okay? But for now, segmentation is simply figuring out different materials. So you can assume a segmentation being tags, okay? So this is liver, this is heart, this is kidney. So liver 1, heart 2, kidney 4, okay? That's a segmentation. Okay, so if I apply to liver red and to heart green and to kidney blue, whatever, okay, so that would be a reasonable thing to do for pre-shading. So I first interpolate the color, I first assign the colors and then I interpolate the colors. Okay, so whether I want to interpolate these tags at all, is whether I linearly want to interpolate it is a question for itself. But if I would have done say this for this as a post-shading step for a segmented data set, that wouldn't have made any sense. I remember heart 1, liver 2, kidney 3, right? If I now first interpolate the values, then between 1 and 3, there's going to be a 2 somewhere in time. But that doesn't make any sense, right? Why should liver between heart and kidney just because I interpolate? Okay, so you see, there's some values where interpolate per se is kind of questionable things, but in particular in those cases, post-shading doesn't make any sense at all. Okay, so we don't want to create any new values and then apply colors to them. In other situations, it might make more sense. Okay, so as I said, no right or wrong, it just depends on the situation. Now, since I talked about segmentation already, so let's just have a slide on that. So here's one of those examples of a segmented data set. So again, it's grouped, and that grouping can be based on very complicated metrics, not just the Hounsfield unit of the CT scan. If you remember my stream on computed tomography, you can probably remember that the Hounsfield units for pretty much any organ is the same anyhow. Okay, so we can't use CT to distinguish organs. We have other metrics. Again, there's MR, wouldn't help much with organs either. I can give you that much, but there's contrast agents. So anyways, we have, or let's say not we, but the medical practitioners, they have a lot of tools to distinguish organs, but the best tool is just, look at it. Okay, so if you look at a data set, any reasonable practitioner, any reasonable doctor would not have a big deal of identifying that organ. Okay, so hopefully no one's going to mistake that for a bladder. If yes, you should leave that a practitioner's office right away. Okay, so bottom line is, so it's actually there's more in a data set than just the values. Okay, so there's a location. Okay, so I mean, if a train ran over you and you're still alive, then there might be issues with that. And as a matter of fact, that is. So that often happens. That, for instance, if there's some genetic disease that someone's suffering from, then, for instance, in particular, things like the appendix can be located pretty much randomly in the body. And then that's actually the situations where doctors run into trouble figuring out where's that appendix. It can be pretty much anywhere. So from what I heard is from practitioners, there's situations where your appendix can be pretty much anywhere in your body. So, and that's a big deal. But for at least normal things, the heart, the lungs, they're pretty much where they're supposed to be. So the bottom line is, if you take a data set, if you take a CT scan data set, you will probably not be able to tell difference from the values. But the fact that there's a value of 5 here and the fact that there's a value of 5 here will still allow you to say, well, okay, that's the bladder and that's the heart. Okay, but that, as I said, requires requires a lot of additional information. Like, for instance, knowledge of an anatomical atlas. What this means in syntactical point, like just in like numbers, this means that we take, in addition to the values, we take the position into account. Now, well, I mean, the position of the heart might differ a little bit. So you also take interface information into account. You would say, okay, well, okay, here's my value of 5, and the lungs are also value of 5. I mean, lungs are easy to determine because they're filled with air, but let's just pretend they aren't. Okay, so you say here's 5 and here's 5, but I got the 4 in between. So I just consider this an interface, and everything on the left of that 4, I call it heart. Everything on the right of that 4, I call lung. Okay, so it's position information, it's interface. Interface means gradient, it's gradient information. So long story short, it's a thing that is complex, but once we've done that, either manually or automatically or semi-automatically, right, via some things like blood fill or so, I can literally color every voxel. I can say, well, that's hard. And as a matter of fact, that is being done by poor medical science students. Okay, so you have like a herd of medical science students doing these anatomical atlases sometimes. Okay, so at some labs you have folks that sit there that have some basic understanding of human anatomy, and you'll just have them sit there and color objects voxel by voxel, and then you combine these voxels into a big data set, and then the professor is going to sell that for millions of dollars to someone else. This is how this sometimes works. Okay, so but that's a segmentation. Okay, and that's different from the classification from before. The classification is done by the means of a transfer function. This is done by the means of whatever, literally whatever. You can take into account whatever you want, and part of what you take into account is like common knowledge, and that's hard to model. I guess state of the art is moving from manually more and more to automatic methods, but it's hard. It's a very hard process because of noise, all kinds of things. So I'm not aware of any like completely automatic segmentation approach for a human body. So they're generally still semi-automatic, they're supervised. You're able to segment based on location, but also on things next to a different blank area between. The tool lets you separate them. Yeah, so that's what I said. So that's basically, I mean, in syntactic terms, that means gradient, right? You use the location, use the value, and use the gradient. Right? Whereas gradient is a fancy term for interface, right? If you have a high gradient, we call this an interface. But this is actually easier said than done. Once we get to the point in the exercises where you have implemented the direct volume render, which is one of the upcoming assignments, we can give you data sets of actual humans, and you can go through these data sets and look at them and try to figure out if you find the interfaces. And the trouble is, it's actually pretty hard. It's actually fairly hard to find interfaces between tissues. I mean, and the funny thing is, it's not only hard, from what practitioners tell me, for certain tissue types, it's not only hard to find them in the data set, but it's also hard to find them in the actual open body, right? I mean, brain is a particularly good example. It's pretty hard to find anything in this like grayish, whitish matter, okay? So it's a non-trivial process. Okay? But yeah, you can use various metrics, but sometimes again organs touch each other, so interfaces might be gone because of limited resolution of your scan. Not easy. Okay, let's come back for the last few remaining minutes of today's stream. Let's come back to a few details on direct volume rendering. I said I want to start with direct volume rendering, so let's talk about this a little bit. So, like what I said is we need to take the data and map it to something that has a visual meaning, or more specifically, to optical properties. Okay, I already introduced this idea of color and opacity. But we need a little bit more, okay? So we need, I put it here, we need an optical model, okay? So I mean saying, okay, well, this Hounsfield unit, I don't know, 7, we map this to red and 20% transparent. That's okay. So now we've moved from this regime of just numbers to something that has a visual meaning. But now we need to do the second step. We need to somehow turn this visual meaning into values. Okay, just because something is red and 50% transparent doesn't give me the color of a pixel on a screen, or the color in a video or whatever, right? So what we need is some sort of optical model that tells us, okay, like we don't need physics, we need optics here, right? We need to say, okay, this is a point of, this is a piece of, I don't know, aerogel. This is a piece of red aerogel, and this is a piece of red aerogel that, due to its molecular structure, is 80% transparent. Okay, then we need to look this up in, I don't know, some optics book, some physics book that tells us, okay, if that's the case, what's this going to look like? How is a beam of light going to interfere with that, and how do we perceive that? Okay, so in essence, what we need to sum things up here for a second, to directly render a volume is, you need your data, you need to have this mapping, this thing that we call transfer function, and you need to have some optical model. Okay, you can't just say that's nature, go. I mean, you have to compute this somehow, right? You need to have an optical model, and generally these optical models are some sort of a PDE, partial differential equation, or some crazy equation, and we need to find a numerical solution for that. Okay, so that's pretty much what's left to do, and then we'll be done with direct volume rendering. Okay, so how do we choose? Okay. How do we choose, which optical model do we choose? Okay, and here I've picked a few things, computer generated or photographed things, of real semi-transparent thingies. Okay, so those aren't aerogel, those are things that are a little bit more like, I don't know, down to earth. Fire, right? I mean, fire is kind of this cloudy thing, like literally clouds are cloudy things, or smoke. Okay, in the center you just got smoke, it's not fiery smoke, it's just smoke that's rising and forming a, well, smoke cloud, I suppose, around a cylinder. So all of those are computer generated. So apparently we have, all those images here are computer generated. So apparently we have an idea how to map those quantities to, those optical quantities to an image. Okay, and that sounds actually more simple than it really is. So let me just give you a brief glimpse into some of the optical models, some of the more simple optical models. Okay, so what we can do is we can, first of all, distinguish two things that can happen. Okay, one is emission, so we can have a point glow by itself, and one is absorption, so we can have a point in space take away energy. Okay, so it doesn't take it away, it converts it to heat in general, but let's just say energy is converted into something that we don't see anymore, and energy is converted from something that we didn't see before. So we get more light and less light. Okay, so now let's look at what can happen. So we can have a point in space, the volume, that glows into a particular direction. So I only care what's going on in one direction because I'll be looking along that direction later on. So that point might glow, okay? Then it gets brighter. What also can happen is that this point absorbs. So this, for instance, could be a reacting a molecule, so a piece of the fire that just glows, okay? Well, subsurface scattering, it's another thing. No surfaces here, so no subsurface scattering. So that's good for a second, okay? But this is along the same lines. It's just for a different type of thing. It's not for volumes, it's for, well, usually surfaces. But then again, we could assume that it's a volumetric thing. But long story short, yeah, same thought, it's just different situation. Okay, so let's keep things simple. They get complicated enough already, believe me. So the first thing is we can have a piece that glows, again, fire, right? Might just emit light at some places in the volume, or this would be a particularly good example for a smoke particle, right? You got, I don't know, some ash particle rising, and then there's light from behind that ash particle, maybe from a fire that's burning here, or maybe just from background illumination, and that's just diminished, it's reduced because it's absorbed. Okay, so we have emission and absorption, and then we have this thing called scattering. In this case, it's not like energy or light is created from other forms of energy or is taken away, but it's just changed in direction, which has a similar effect, right? If we're looking this way, and there's light coming from here, and it's not absorbed by this particle, right? So that might be, like, think about this as a prism, right? It'll just kind of spread the light out. It'll just scatter it into various directions. Then we kind of get the same effect. So the incoming light is reduced and we see less. It's darker, to make things simple. Okay, and the same is something similar is true for inscattering. So we've got light coming in, and that gets scattered all in the same direction. So the point appears brighter, despite the fact that it doesn't glow by itself. It just kind of shifts the direction, changes the direction. Okay, so those are simple things that can happen. And that's not even taking into consideration that we have different frequencies of light and crazy things going on. Okay, but overall, this idea of emission absorption due to active emission absorption or due to scattering effects captures a lot of the things that we encounter in reality. Okay, so that captures a lot of the fiery phenomena, a lot of the cloudy phenomena. Okay. Now the question is, which of these four things do we intend to simulate? Okay, so we could do absorption only, emission only, so basically only consider one of those four corners. We could do absorption and emission, only the active parts, okay? Or we can consider the scattering, maybe like how many levels of scattering do we want to consider, right? I mean, do we just want to consider light scattered once or multiple times or whatever? And what's sort of the gold standard these days for scientific visualization, remember that's scientific visualization here, we're not dealing with effects or so, is to only consider absorption and emission, to ignore the scattering term completely, but only look at the two active absorption and emission terms. And there's a little bit of a debate these days going on. So basically, if we go through this like set of things here from top to bottom, we could say, well, that's fewer, less realistic, more realistic, faster to compute, slower to compute, right? And wherever you are, wherever is acceptable in terms of computational power, obviously depends on the power of your machine. So we're currently at this point where we can achieve acceptable, meaning interactive performance somewhere around here. Okay, so scattering is actually possible to compute. Still, in most cases, you only do emission and absorption for scientific visualization. And the question is why? I mean, if this here is more realistic, why not consider it? And the point is very simple. Like, what does realistic even mean? I mean, it's cool that we get a realistic cloud rendered, but remember, the data set isn't a cloud. It's a CT scan of a human, okay? So just getting the CT scan, just getting the human rendered properly as if it would be a fire or a cloud doesn't necessarily make a lot of sense, right? Because the human is no fire or cloud, hopefully not. Okay, so what we ultimately want to do is not get a photorealistic image, but we want to answer a question. We want to know, where's that cancer? How is that fracture cured the best? Okay, where did the liver go in that person? Right? That's a valid answer, right? Question. Or where did that, I don't know, where did this machete punch through, right? Think about crimes, right? So, or think about accidents, okay? What did this bullet puncture, right? In that case, it doesn't matter if the body is rendered in its full, I don't know, as if it would be burning fidelity. The only thing that matters is, did this bullet puncture the heart or something? Okay, so in that case, so far it turns out, I mean, it's still to some degree an open question in research, but so far from what we know, it turns out that using any of these things creates more trouble than it helps. Right? Because, well, literally, if you consider scattering, you start to see shadows, right? One thing shadows another. And you know that, like, you got a shadow on the lung, which is generally not a good diagnosis, right? You might have cancer in that case or some other object in the lung. So as a matter of fact, these shadows are if we just use emission and absorption, they're actually part of the diagnosis. So if we add them from shadowing, from scattering, they might actually make it harder to interpret things. And that's sort of the state of the art. So right now, even though we can't do it, I'm aware of systems that do it, it's actually not too hard to implement. It's a little bit harder to get it fast, but nonetheless, you can do it. But I'm not aware of any like production system in, for instance, medical science that uses for other than cool effects uses those features. Okay, so next stream, next week, next Monday, I'll continue to explain how using that emission absorption model, we will derive a mathematical or physical formula how light interacts with matter that just emits and absorbs light. And from that we'll derive a numerical approximation of that formula, which we'll then use to compute direct volume rendering. Okay, so that's kind of where we're heading. And that's it for today's stream, unless you have any remaining questions. So are there any questions? So it doesn't seem to be the case. I mean, we've got the, if you have any questions, we've got the exercise coming up as well. And you've got the assignment coming up with this marching squares assignment that I said I highly recommend. Generally, I highly recommend to participate in assignments. But if you want to get more insight to what I just presented, go ahead. Where would I find the assignment information? On Moodle. So if you're a student at University of Duisburg-Essen, you'll find them on Moodle. If not, then boom. You can look at you can at least look at the source code, which is on GitHub. But the assignments themselves are on our university systems for the students. Okay. And those are in the Moodle course corresponding to our to this class. In case you haven't noticed, that's an actual class. Okay. Good. If there are no further questions, GitHub, yeah, it's under, maybe someone can post the GitHub URL here. Yeah, it's under my name. It's under, well, it's under GH, or I think it's something like Jens der Krüger or so. But you should be able to figure that out. I'm not sure if it's linked here in Twitch, but yeah. If you look at my other stream, that you'll have an URL once I'm done here. You can also take a look at my private stream that I stream later, and that has a link to the GitHub URL. Well, seems like bot isn't working, huh? Or it's not connected to the stream. Okay, yeah. So just look at the I'm done image in a couple of seconds, and that has another stream in it. Okay, here it is. Thanks. Yeah. So there you'll find the VIS assignments. Okay, then that seems to be all for today, at least for the stream. Again, there's an exercise coming up for the student of the University of Duisburg-Essen. And that's it for today from my side. So thanks for listening. As usual, bye-bye. Stay healthy as soon as you can. Get vaccinated. See you next week.